Question 7. Particles A and B are attached to the ends of a light inextensible string. The string passes over a smooth fixed pulley. The particles are released from rest with the string taut and A and B at the same height above a horizontal floor. In the subsequent motion, A descends with acceleration 1.4 meters per second squared and strikes the floor 0.8 seconds after being released. It is given that B never reaches the pulley. Part 1 says calculate the distance A moves before it reaches the floor and the speed of A immediately before it strikes the floor. Right, let's begin by writing down the things we know. So for particle A, we'll write down suvat. Displacement is something we're trying to find, the distance moved by A. We know that in the question it says the particles are released from rest, so U is 0 meters per second. V is another thing we're trying to find. Acceleration is given in the question. It says A descends with an acceleration of 1.4 meters per second squared. And we know that particle A strikes the floor 0.8 seconds after being released. Let's begin by finding V, because we know that V equals U plus A T. So U is going to be 0, so all we need is A, which is 1.4, multiplied by T, which is 0.8. So 1.4 times 0.8 is going to be 1.12 meters per second. Now let's try and find S. So we know that S equals UT plus half AT squared. We know that U is 0, so this term will disappear. So we get half multiplied by A, which is 1.4, multiplied by 0.8 squared. So 0.5 times 1.4 times 0.8 squared gives us 0.448. So the distance moved by A is 0.448 and the speed of A immediately before impact is 1.12 meters per second. In part 2, we need to show that B rises a further 0.064 meters after A strikes the floor, and we also need to calculate the total length of time during which B is rising. Well, I've borrowed our answer from the previous part here. So just before impact, all of these were true for particle A. We're now interested in particle B. And in particular, from the values here, we're going to be interested in the final velocity. Because remember, this string is inextensible, so whatever speed A is travelling at downwards, B has to be travelling at the same speed upwards while ever this string is taut. And this string will be taut all the time where A is moving down. However, when it touches the floor, any time after that, the string will no longer be taut because B will be coming up here and A will no longer be moving downwards. So let's write down our suvat for particle B. So here we're going to be looking at what happens after impact. So at the instant of impact, we know that B is going to be moving with a speed of 1.12 meters per second. So that's going to become our initial velocity. If we're interested in the highest point that B reaches, then, well, we want to know the point when the velocity is 0. Because if it's got a velocity upwards, then it's going to get higher. And when it reaches its highest point, every point after that on the way down, it will have negative velocity. So the highest point will be at a velocity of 0 meters per second. We also know acceleration because now that A is touching the floor, there is no tension in the pulley. So the acceleration will be purely due to gravity. Now because I've defined U as positive, so if U equals 1.12 is going upwards, that means I have to have gravity coming in the other direction, which has to be minus 9.8. So I have to be consistent with my use of the minus sign here. So acceleration is minus 9.8 meters per second squared. S is what I'm trying to find. It does give me the answer in the question, but I can't assume that's true. I have to show that that's true. And we don't have a value for time either. So we're interested in finding S. We're going to use these three here. We're going to use V squared equals U squared plus 2AS. So V squared is going to be 0. U squared is 1.12 squared. And 2AS, well, considering A is negative, I'm going to write a minus sign here. So 2 times 9.8 S. So let's rearrange it a bit. We're going to get 19.6 if we do 2 times 9.8. S equals 1.12 squared. If we divide through, we get S equals 1.12 squared divided by 19.6. So 1.12 squared divided by 19.6, and we get 0.064 as we expected. We also need to calculate the total length of time, and in order to do that we are going to use V equals U plus AT. So remember, V is 0, U is 1.12. Considering acceleration is negative, we may as well write it minus straight away. So 9.8 t. So 9.8 t equals 1.12, and t equals 1.12 divided by 9.8. So 1.12 divided by 9.8 is 0.114. However, this isn't our final answer for t, because we want the total length of time during which B is rising. So the total time will include this 0.114, but it was also, as we know from part 1, rising for 0.8 seconds before A hit the floor. So we need to make sure we add on that 0.8. And so altogether we get 0.914 seconds for the total time that B is rising. Question 7, part 3. Sketch the velocity time graph for the motion of B from the instant it is released from rest until it reaches a position of instantaneous rest. So let's have a think about what's happening in this diagram. Both particles are released from rest, and A is going to move towards the floor and B is going to move upwards. It's important to note that because this string is taut, the speed that A moves down towards the floor is always going to be the same at any point as the speed that B moves up towards the pulley. Part way through, A is going to hit the ground. At that point, the string is no longer taut and B is going to move up a little bit more before it moves back down. We're only interested in B moving upwards until it's at its very highest position, where it's at instantaneous rest. So let's look at some information we figured out from earlier in the question. In part 1, we figured out the velocity of particle A when it hit the floor. But we know that B will be travelling at the same speed. So the speed that A hits the floor is 1.12 meters per second. So at that instant, B must also be travelling at 1.12 meters per second. So let's say before impact. And for particle B, the initial speed will be 0 meters per second. Its final speed will be 1.12 meters per second. As well as the initial and final velocity, we know from in the question that it takes 0.8 seconds for this to happen. So this is what you could consider the first part of the journey, because there's another part that's going to be slightly different, because after impact is what we were doing in part 2. So immediately after impact, the velocity is 1.12. That now becomes our initial velocity, 1.12 meters per second. And we worked out in part 2 that the time that it's going to be going upwards for after A has hit the ground is 0.114. We also know that when B is at instantaneous rest here, it's when it's at its highest point. At that point, V is going to be 0. So now we can go ahead and draw our velocity time graph. So V up the side, T across the bottom, and we can see that the velocity is going to increase from 0 to 1.12, and before impact it's going to do that over 0.8 seconds. So we're going to have a line with positive gradient, and then after impact it's going to go back down from 1.12 to 0 over a much shorter time. Therefore, this part of the graph must be steeper than this part of the graph, and significantly so. So remember, our velocity starts at 0, so we're going to start down here. We're going to have a reasonably shallow part of the graph followed by a fairly steep part of the graph. Remember, whenever you draw a velocity time graph, you should mark on any points of interest. So I'm going to use some dotted lines here to help me do that. I've got a time down here of 0.8 seconds and a time here of 0.914 seconds, and we have a velocity of 1.12 meters per second. So it is important that you label these 3 points on the graph, or you're going to end up losing marks. Okay, so that's our velocity time graph. Question 7, part 4. Before A strikes the floor, the tension in the string is 5.88 newtons. Calculate the mass of A and the mass of B. Well, whenever we have a pulley, the tension in the string either side of the pulley is equal. So we could draw a tension force on either side of the pulley, which we can call T. If the string is taut, the acceleration of particle A down will be the same as the acceleration of particle B in the upwards direction. So whenever we've got a connected system, as in one particle connected to another in some way, it's useful usually to consider each particle separately. So let's start off by looking at particle A. So here is particle A, and we've got two forces acting on it. We've got a weight downwards, which is going to be equal to mg, and we have a tension in the string pulling upwards, which we will call T, and we know that that is equal to 5.88 newtons. We also know there's an acceleration. For particle A, the acceleration is downwards of 1.4 meters per second squared. So let's resolve forces in a vertical direction. Let's take downwards to be positive because that's the direction of the acceleration, and we've got our weight, which is mg. In the opposite direction, we've got our tension, which is 5.88 newtons, and that's going to equal mass times acceleration. Well, mass we don't know, but acceleration is 1.4, so that's 1.4 m. If we rearrange this, we can get mg minus 1.4 m equals 5.88, and then we'll factorise. mg minus 1.4 equals 5.88, and then we'll divide through to get 5.88 divided by g minus 1.4. Let's work out what that is. So we've got 5.88 divided by 9.8 minus 1.4. and that gives us a mass of 0.7 kilograms. So the mass of particle A is 0.7 kilograms. Let's now consider particle B. And we'll find that we have a very similar calculation, but we need to be careful with signs. So here's particle B. The forces are going to be very similar. We're going to have mg for the weight, although the mass this time will probably be different. We're going to have tension in the string going upwards. Tension this is the same because it's got to be the same either side of the pulley. So 5.88 newtons. So let's once again resolve in the vertical direction. This time forces going upwards that are positive. We've got the tension, which is 5.88. In the opposite direction we've got mg, and that's going to equal ma. Well, a is 1.4, so again on this side we get 1.4 m. Rearranging, we get 5.88 equals mg plus 1.4 m. Factorising gives us mg in brackets plus 1.4, and then divide through, we get m equals 5.88 over g plus 1.4. So a very similar calculation to what we did before. In fact, we can just modify it slightly in our calculator to save some time, and we get 0.525 kilograms. So the mass of particle B is 0.525 kilograms. Question 7, part 5. The pulley has mass 0.5 kilograms and is held in a fixed position by a light vertical chain. Calculate the tension in the chain, and in part A it says immediately before A strikes the floor. So let's consider just what's happening with the pulley. So we're just going to have all the forces that are acting on the pulley. We're going to have either side of the string, and we know from before this has a tension of 5.88 newtons in each part. It says it's held in a fixed position by a light vertical chain. So the chain is going to provide an upward tension here, which we will call T. We've also got the mass of the pulley, which is going to be a force downwards here, which is going to be equal to 0.5 G. So we've got four forces acting here, and the pulley's not moving, so there's no acceleration. So these forces must all be in equilibrium. So resolving in a vertical direction, we'll take upwards to be positive. We'll get T minus 2 lots of 5.88 minus 0.5 G, and that has to equal 0. So T equals 2 times 5.88 plus 0.5 G. So 2 times 5.88 plus 0.5 times 9.8, and we get 16.7 newtons if we do that to three significant figures. In part B, we're interested in what happens immediately after A strikes the floor. So when A has hit the floor, there will no longer be any tension in this string. So the only forces we have acting on the pulley are T going upwards and the weight going downwards, so 0.5 G. So this could quite possibly be the easiest question in the paper. There's no acceleration, so resolving vertically, we get T minus 0.5 G equals 0 because there's no acceleration on the pulley. So T equals 0.5 G, which is just going to be 4.9 newtons. And that's the end of the paper. Thank you for watching, and I hope it's been helpful.